Section: Introduction. In this section, we introduce the importance of search in AI problem solving. A prominent example is IBM's Deep Blue, which used a powerful search algorithm called alpha-beta pruning to defeat world chess champion Garry Kasparov in 1997. Search techniques are also applied in neural networks, as seen in AlphaGo and its successors, where a value network guides the decision-making process through a method known as Monte Carlo tree search, MCTS. This approach allows for future predictions to refine decisions iteratively. Recent studies on large language models, LLMs, show a similar framework, but the one-step autoregressive policy only addresses part of the problem and struggles with complex tasks, revealing limitations in long-term planning. The reliance on explicit search can lead to errors and increased costs, especially if the value model is inaccurate. Therefore, we ask, can a policy model independently predict and use future information to enhance its predictions without needing explicit search during inference? Our paper investigates the shift from explicit search algorithms like MCTS to an implicit search method that teaches the policy to predict and utilize future outcomes. To simplify future predictions, we draw inspiration from diffusion models, which generate samples through a multi-step process. We refine our policy predictions using a bidirectional self-attention mechanism alongside this diffusion process. We represent the future through interactions between the policy and the environment, making the future generation akin to implicit searching. We name our approach DIFFUSEARCH, which explores future possibilities through diffusion modeling without explicit search. Unlike traditional methods that separate the world model from the policy, DIFFUSEARCH integrates the world model directly into the policy, eliminating intermediate steps. We compare explicit search via MCTS with our implicit search through discrete diffusion, focusing on chess, where explicit search is crucial. The insights gained here may also apply to natural language tasks. Our experiments show that DIFFUSEARCH improves action accuracy by 19.2% over the one-step policy and by 14% over the MCTS enhanced policy. It also enhances puzzle-solving abilities by 30% compared to the MCTS policy and achieves a higher game-playing skill, reflected in a 540-point increase in ELO rating. Our contributions include 1. Proposing DIFFUSEARCH as a way to leverage future information through diffusion modeling instead of explicit search. 2. Demonstrating its superior performance in chess. And 3. Providing a thorough analysis of future representation and diffusion modeling, highlighting its advantages over MCTS-based policies. These results suggest a promising transition from one-step policies with explicit search to a future-aware multi-step diffusion policy with implicit search capabilities. Next, we will outline key concepts and notations relevant to the chess playing problem and diffusion modeling. In chess, we operate within a framework of alternating Markov games, characterized by a state space, an action space, a state transition function, and reward functions for both players. The goal is to develop a policy that maximizes the final outcome based on these elements. Section Summary. In this section, we introduce DIFFUSEARCH, a novel approach that leverages diffusion modeling to predict and utilize future information for action prediction in chess, moving away from explicit search methods like MCTS. Our method demonstrates significant improvements in action accuracy and puzzle-solving capabilities, outperforming traditional one-step and MCTS enhanced policies. Section: Discrete Diffusion Modeling. In this section, we discuss discrete diffusion modeling, which is a type of latent variable model that includes both a forward and a backward Markov process. We start with a discrete random variable, represented as a one-hot vector, that can belong to one of k categories. The forward process takes our original data and transforms it into a series of increasingly noisy variables. The backward process, which we learn, works to gradually remove this noise and return to the original data distribution. To optimize our generative model to match the data distribution, we typically use a variational upper bound on the negative log likelihood, since direct calculations can be complex. In our discrete diffusion approach, both the forward and backward processes are defined as categorical distributions. This allows us to calculate the forward process posterior and each KL term analytically. Next, we introduce DIFFUSEARCH, our method that predicts future scenarios using discrete diffusion modeling, specifically for chess tasks, without needing explicit searches during inference. We train our model in a supervised manner, using the current state as a historical representation. For future representations, we explore various options, including future actions, action states, and action state values. Ultimately, we select the action state approach for its effectiveness and simplicity. For training, we utilize a supervised approach with Stockfish, the strongest chess engine, to label board states from randomly selected games. We aim to approximate the optimal policy and construct a dataset that captures the best future moves based on evaluations. However, we find that directly predicting the entire future sequence can hinder learning, so we turn to diffusion modeling, which offers strong sequence modeling capabilities. We implement a weighted cross-entropy loss for our diffusion model, simplifying the KL term for each random variable. This involves a time-dependent reweighting term that adjusts the importance of noisier variables. To facilitate conditional training, we freeze the state tokens and focus on denoising the next action and future tokens. We also use Monte Carlo sampling during optimization. Further details and derivations can be found in the appendix, and we outline our training procedure in the algorithm section. Section Summary. In this section, we introduce discrete diffusion modeling as a latent variable approach that uses forward and backward Markov processes to transform and denoise data, specifically applied to our DIFFUSEARCH method for predicting future chess moves. We detail our supervised training strategy utilizing the Stockfish engine to label board states, and we optimize our model using a weighted cross-entropy loss to enhance action prediction while considering future information. Section: Inference. In this section, we discuss our inference process. During inference, we determine the best action by maximizing the probability of an action given a state, which requires considering all possible future outcomes. However, this becomes impractical as the number of future possibilities grows exponentially with the horizon length. For example, in chess, the game tree can have over 1 billion nodes. To simplify, we focus on the best future outcome for each action, represented by the joint probability of the action and future states. We then maximize this joint probability without needing to consider all future possibilities, which we can achieve by sampling from our trained model. For our diffusion sampling, we use a straightforward decoding strategy that performs better than random decoding. Specifically, at each diffusion step, we reset the least likely tokens to a noise state. To explore different search depths, we train separate models for various horizon lengths and also examine a single model with mixed horizon lengths. Next, we compare our model against 3 baseline transformer models: the state action model, which predicts the next move through behavioral cloning; the state value model, which evaluates the value of future states; and the action value model, which assesses the value of each legal action in the current state. We also incorporate the trained state action and state value models into Monte Carlo tree search, MCTS, as done in AlphaZero. For our dataset, we gathered games recorded in February 2023, using up to 100,000 games for scaling analysis and reverting to 10,000 games for other experiments due to resource limits. We convert centupon evaluations from Stockfish into win percentages and categorize them into 128 bins for our state value models. We represent the game state as a fixed-length string and store actions in a standardized notation. In terms of implementation, we utilize the same GPT-2 transformer architecture for all neural models to ensure a fair comparison. We modify the attention mechanism in DIFFUSEARCH to enhance performance without adding new parameters. We train all baseline models until they converge, setting a maximum of 200 epochs for diffusion models due to their slower convergence rates. We use the Atom optimizer with a learning rate of 0.0003 and a batch size of 1024. Our default settings include a horizon of 4, 8 network layers, 20 diffusion time steps, and a specific noise type. We perform 100 simulations in MCTS and adjust exploration parameters based on a validation set. For evaluation, we focus on three main metrics: action accuracy, which measures how often our model selects the correct action; puzzle accuracy, which assesses how many puzzle solutions our model matches exactly; and tournament ELO, which calculates ratings based on internal tournaments where each policy plays against others. Section Summary. In this section, we describe our inference process in DIFFUSEARCH, which simplifies action comparison by using joint probabilities to avoid intractable marginalization over future states. We also outline our experimental setup, including baseline models, dataset construction, implementation details, and evaluation metrics to assess the performance of our approach. Section: Main Results. In this section, we present our findings on the prediction and playing strength of our model compared to baseline models, as shown in the table. We also include the performance of Stockfish 16, which serves as the oracle for our dataset, with a time limit of 0.05 seconds per legal move. We observe that DIFFUSEARCH significantly surpasses the SA model by 653 ELO points and achieves 19% higher action accuracy, demonstrating its effectiveness in enhancing next action predictions through future forecasting. Notably, even with 20 times fewer data records than the SAV model, our model still performs better, showing about 10% higher action accuracy. Additionally, we outperform the MCTS-based agent by a difference of 542 ELO points and an increase of 14% in action accuracy, highlighting DIFFUSEARCH's strength in modeling multi-step simulations compared to the step-by-step MCTS enhanced policy, which requires a careful balance between policy and value models. We also compare various baselines and future paradigms during the training of DIFFUSEARCH with a horizon of 4. We find that directly predicting future actions with DIFFUSEARCH SA negatively impacts performance compared to SA, likely due to the challenges of predicting future moves in chess. However, when we incorporate future states, we see significant performance gains, such as comparing SA to SASA and SAVAV to SAVSAV. No further improvements arise from integrating values in DIFFUSEARCH, possibly because we train on the optimal future trajectory rather than all possible ones. When using an autoregressive transformer, we note that overall performance is around 26%, which is better than SA's 22.1% due to the use of more SA pairs. However, this still falls short of DIFFUSEARCH, emphasizing the need to model bidirectional context to utilize future information effectively. Next, we explore the impact of future quality on performance. We denote a sequence of future Horizon 2 as a series of states and actions derived from a world dynamic function and a policy function. Initially, we use random state action sequences, which do not improve performance. We then try selecting random actions and using the resulting states from those actions, which shows better results. This highlights the importance of aligning states with their corresponding actions. Finally, we incorporate high-quality future actions suggested by Stockfish, leading to further performance improvements over the random action selection method. Lastly, we investigate different training methods using our dataset annotated with future states and actions. We find it challenging to train the model to output the entire future sequence directly, resulting in lower performance compared to autoregressive training. We also test continuous Gaussian diffusion and find it performs better than direct and autoregressive methods, but not as well as discrete approaches. We discover that an absorbing diffusion with a reciprocal function significantly outperforms continuous diffusion. Furthermore, a linear function exceeds both constant and reciprocal methods, as well as the multinomial approach. Section Summary. In this section, we present our model, DIFFUSEARCH, which significantly outperforms baseline models, achieving a 653 ELO increase and 19% higher action accuracy compared to the SA model, despite using 20 times fewer data records than the SAV model. We also highlight the importance of future state integration and high-quality action selection, demonstrating that proper discrete diffusion modeling enhances performance over other training methods. Section: Does DIFFUSEARCH predict accurate future information? In this section, we examine whether DIFFUSEARCH can accurately predict future information. We analyze the percentage of valid actions and compare them to the optimal actions suggested by Stockfish for each predicted action. The best metric, referred to as action accuracy, is defined as the accuracy of the first action, which we find to be nearly 100% valid. As we look further into future steps, we notice a decline in both the valid and optimal action rates. However, even at the third step, where the valid rate drops to 50%, it still exceeds the random move baseline of about 1.6%. This suggests that our model maintains some predictive ability for future moves, even if its performance decreases. We also see that the accuracy of predicted states is perfect for the first state but decreases for later predictions. In our appendix, we show that increasing the training data improves the world model's effectiveness in DIFFUSEARCH, achieving over 90% accuracy in predicting valid future states. Next, we discuss how DIFFUSEARCH utilizes future information. We attribute this capability mainly to the self-attention mechanism and the iterative decoding process. When we use a single self-attention layer, our model performs worse than the SA model, but it outperforms it with 2 layers, and performance continues to improve with more layers. This indicates that additional layers allow for better interaction between subsequent actions and future predictions. We do not see a similar improvement in the SA model with more attention layers, possibly because the available data does not require it. Furthermore, we find that using a suitable decoding strategy enhances next action predictions as the number of iterations increases, although the improvement is modest compared to adding more attention layers. We then compare implicit search in DIFFUSEARCH to explicit search using MCTS. In DIFFUSEARCH, deeper searches are achieved by increasing context length, while MCTS relies on running more simulations. Our results show that DIFFUSEARCH significantly improves with increased search depth, while MCTS performance plateaus after about 50 simulations. This stagnation may be due to errors from the value network caused by a limited horizon. We also measure latency per move for both transformer with MCTS and DIFFUSEARCH on a single GPU. We find that the transformer with MCTS is heavily impacted by the need to call the value network for each simulation, while DIFFUSEARCH only experiences a slight increase in latency. Regarding scaling, we observe that increasing the dataset size positively impacts DIFFUSEARCH's performance. We conduct experiments with the DIFFUSEARCH's ASA model and the transformer SA using game sizes from 5,000 to 100,000. Both models show a log2 scaling behavior, indicating that doubling the training data leads to a linear increase in accuracy. This scaling also significantly enhances future predictions, resulting in more valid and accurate representations of future actions and states. Finally, we conduct a case study using challenging puzzles from Lichess to compare DIFFUSEARCH and the transformer, SA. We present 2 examples, with more in the appendix. DIFFUSEARCH shows better foresight, accurately predicting key exchanges and sacrifices that lead to long-term advantages. In one puzzle, DIFFUSEARCH sacrifices a rook to create a long-term checkmate threat, forcing the opponent to defend and allowing for advantageous exchanges. In contrast, the SA model makes a critical mistake by focusing solely on immediate checkmate without considering counterattacks. Similarly, in another puzzle, DIFFUSEARCH correctly anticipates a sacrifice for long-term positional benefits, while the SA model misjudges the exchange's value, resulting in poor moves. These results highlight DIFFUSEARCH's effectiveness in long-term planning without relying on explicit search. Section Summary. In this section, we analyze the predictive accuracy of DIFFUSEARCH, finding that while the validity of predicted actions and states decreases with each step, it still significantly outperforms random moves. We also demonstrate that DIFFUSEARCH's future-aware capabilities are enhanced by self-attention and iterative decoding, and that scaling the training data improves its performance in predicting valid future actions and states. Section: Neural Networks for Chess. In this section, we discuss the evolution of chess AI, which has shifted from manually designed search strategies to more data-driven, learning-based methods. Early efforts, like Turing's work and NeuroChess, relied on crafted algorithms, leading to advanced engines like Deep Blue and Stockfish. The introduction of neural networks, particularly with AlphaZero, changed the game by using deep reinforcement learning and Monte Carlo tree search to develop its own heuristics, such as policy and value networks, without manual input. The rise of large language models has also influenced chess AI, allowing for new ways to evaluate and interpret chess play, integrate text data into training, and explore models that do not rely on traditional search methods. Despite these advancements, look-ahead search techniques, like beam search and simple depth-1 search with value networks, still outperform policy models in predicting actions, highlighting the importance of look-ahead information in chess. Unlike previous research, we aim to teach the policy model to look ahead directly, removing the need for handcrafted search algorithms or separate value networks. We also explore diffusion models, a powerful type of generative model used in various fields, including image and text generation, as well as reinforcement learning. These models work by gradually transforming random noise into data samples through a multi-step denoising process, which connects to score matching and energy-based models. Diffusion models excel in tasks requiring global control and future planning, such as math reasoning and robot manipulation. We note that DIFFUSEARCH incorporates a world model within the policy, which we find essential. The main purpose of a world model is to understand the environment's dynamics and predict the outcomes of actions in model-based reinforcement learning. A well-learned world model can optimize the policy of a reinforcement learning agent and help it reason about future actions. Traditional world models often rely on single-step predictions, which can lead to compounding errors. Recently, there has been interest in multi-step world models using diffusion models, although these typically separate the world model from the policy. Our approach, similar to diffuser and decision diffuser, integrates the world model with the policy, but we differ in our modeling techniques and training methods. While they use continuous diffusion, we employ discrete diffusion. Additionally, diffuser requires a guidance function for action selection, whereas we focus on modeling the best action and future trajectory based on a given state. Unlike DD, which predicts actions through an inverse dynamics model, we model both future states and actions. To our knowledge, the comparison between diffusion world models and explicit search in complex tasks like chess has not been thoroughly examined.